Hello everyone. My name is Wenlong Wang, and I'm a PhD candidate at the University of Minnesota Twin Cities. So today I'm going to present our work, TieredKV, a tiered LSM-Learned index design for superior performance on storage. So let me first introduce some basic knowledge about the key value store and the LSM. So the key value store is a simple and flexible data storage model which is designed to handle a large amount of unstructured data. And it works like a dictionary where every piece of data is stored as the value, and it could be retrieved using the unique identifier which we always refer to as the key. And the LSM is a data structure that is highly optimized for write requests. It is because it could accumulate many small random writes into large sequential write. And it is also the core engine behind some widely used key value stores like the RocksDB and DynamoDB. So speaking of RocksDB, it is a persistent key value store for fast storage, and its main components include in-memory mem table and multiple levels of SST files, which are stored on disk. So the write process is that we first put the key value pairs into the in-memory mem table, and when the mem table gets filled up, we can flush them into the SST files on disk. And there is a background compaction process, which would merge the overlapping SSTs from a higher level to lower level. And the read request was to query the candidate SSTs from higher level to lower level in order, and it would until it successfully read the target key. So during our analysis on the LSM tree, specifically the RocksDB, we found out there exist two aspects which we could get a better performance. One is the LSM size, because based on our analysis, we found the performance decrease severely with the size increasing. And one main reason behind it is the multi-level read, because each read would potentially reach to the bottom level of the LSM. And so based on the analysis, we could think of some other methods that could be helpful to reduce the LSM size and also optimize the multi-level read at the same time. So that's why we think of the learned index. The key concept of learned index is trying to model the CDF of the sorted array, and based on the model, it could directly predict the data location. The basic workflow of learned index is that given the target key, we plug in the keys into the model. Then the model could output a prediction or a predicted location in the original sorted data. We could vary the model complexity based on the data distribution as needed. The simplest model could be linear regression and can also be as complicated as neural networks. And because the prediction is not always accurate, we may need to load the data in the neighborhood around the predicted location. So here is some analysis about the learned index. So the first advantage of learned index is that it could achieve fast lookup based on the some existing experiments on the existing words. It could achieve up to 3 times faster than the B tree or B plus tree. And the second advantage is that it would use a smaller memory. Based on the experimental result, it only used about 1/10 of the B plus tree. This is because each linear model could consist of only 2 floating points, which could potentially cover a large data range. Also, it comes with some shortcomings. So the first shortcoming is that it requires the sorted and the static array to build the learned index. The second is that it brings the trade-off between model accuracy and the complexity. If we want the model to be more accurate, we need to make the model more complicated, and it would also increase the inference time of the model prediction. And at last, it is not good for new insertion because the insertion would change the data distribution, which is making the model less accurate. Then, after the analysis of this advantage and shortcoming, we could easily find out that the faster lookup and the smaller memory usage is exactly what we need from the LSM. And its shortcoming, which is related to the write request, it is exactly the advantage of the LSM. So basically, we could let the LSM to handle the insertion or any write request. So we could, based on this, we could easily come up with some idea to combine the LSM and the learning index together. Here we also have the third piece of the motivation in our work. So in the updated frequent or space restricted systems, they need some periodical cleanup mechanism to remove those duplicate keys. We typically call it garbage collection process. And after the garbage collection process, it would create a static region, and that static region would only serve for read and won't get any modification because the value log is always append only. And remember that the learning nest requires the static and sorted region when during the construction. So this static region is exactly what we need to build the learning nest. And since this region only serves for read, and the read is also the strength of learning nest, so we could easily come up with the idea to use the learning nest to serve the read for this region. So it comes to our architecture design. So we basically design the tiered storage system. So first of all, we separate the keys and the values, and the values are separated into the value logs, and the keys are partitioned into the LSM and the learning index. So for the read request, we first query the keys in the LSM, and if it is not found, we query it using the learning nest model. And by knowing the offset, the key value pairs could be easily read from the value log. And for the write request, we first put the full key value pairs into the value log in append only mode. And then we would insert the key and offset pair into the mem table, and then flush them into the LSM in the typical LSM manner. So because with time goes on, the number of keys in the LSM would becomes larger and larger. Then we also need some mechanism to periodically migrate the keys from the LSMs to the learning index. So here's comes to our second part of our design. So basically, it is building the learning index during the garbage collection. So as we just mentioned, the garbage collection is a periodical process which reclaim the old duplicated keys in the value log. And it is for better space utilization and can avoid the page fragmentation. And why do we want to build the learning nest during the garbage collection? It is because it would occur the smallest extra cost. It is because during the garbage collection, we need to collect valid key value pairs and temporarily store them into the memory. And what we need to do is only to sort them and build the model of learning nest model based on the sorted valid keys. Then, because those keys would be indexed by the learned model, we don't need to reinsert them into the LSM after the garbage collection. So in the experiments, we first need to compare with our baseline, which is the RocksDB. So we enable the state-of-art RocksDB with the same key value pair, key value separation, and garbage collection mechanism. The only difference is that they do not build the learned index. And for the benchmark, we divide our benchmark into 4 phases, each with 1 million operations. In the first phase, we insert all the key value pairs into the key value store, and in the next 3 phases, we do some operations, include the read and updates. And based on the experimental results, we could see that the TieredKV could achieve up to 1.3 times better performance in the write throughput and 3.3 in the read throughput. And we also did some other experiment about the different write and read ratios, and also use some different data sets, like the ones in the table. They are generated from the SOSD, which contains some skewed data set and is used for benchmarking the learning index. And we also benchmark our design using different workload distributions and different data set size. And also we compare the other state-of-art key-value stores, including the HashKV, the Bourbon, the B+tree, and also some existing work of the on-storage learned index. So here comes our summary. Basically, we propose the TieredKV, which is the first key value store that used the learned index as a tiered index together with the LSM. So it could reduce the size of LSM, and it could accelerate the read request, and it would avoid the heavy I/O of the LSM reinsertion after the garbage collection. And based on our extensive evaluation, we could see that our design could achieve up to 4.3 times faster read and 1.4 faster write over the LSM-based solutions, and can achieve up to 7.9 better overall performance compared to the on-storage learning index. That's all for my presentation. Thank you.